Hi, my name is Jesse Donkervliet. I'm a PhD student in the Massivizing Computer Systems group at the Vrije Universiteit Amsterdam, and I'll be presenting our work towards supporting millions of users in modifiable virtual environments by redesigning Minecraft-like games as serverless systems. I co-authored this work together with Animesh Trivedi and Alexandru Iosup. If you find this work interesting, please get in touch using the HotCloud Slack channel or any of the contact info that you can find at the bottom of this slide. Now, as you may deduce from the title, this work is about games. Gaming is a massive industry. In 2019, its revenue exceeded 150 billion US dollars. Now, to put that number into perspective, that's more than 10 times the US recorded music revenue, and is more than 3 times the global box office revenue, the latter of which is generally considered to be a large industry. Now, within gaming, Minecraft is one of the most popular games of all time. It has sold more than 200 million copies, and there are more than 126 million active monthly players. To put that last number into perspective, that means that Minecraft has more users than an operating system like Mac OS. The popularity of Minecraft has led to the creation of many other games with similar features. And we talk about those games collectively as modifiable virtual environments, or MVEs for short. Now, I'll discuss the exact definition of this a little bit later. But for now, I want to talk about why I think these games are generally beneficial. First, these games provide a new kind of entertainment. Whereas traditional online games allow people to get together to explore worlds together, MVEs allow players to also get together and create worlds together. Second, these games can be used for education, as is done in Minecraft's official education edition, for example. The example on the slide here, History Blocks, is a lesson in which students recreate UNESCO World Heritage sites inside Minecraft's virtual world. Third is activism. In Europe, Minecraft was successfully used to stop illegal logging, and projects such as the Uncensored Library allow players to read texts that have been censored by their governments. Finally, I think Minecraft and MVEs are able to bring people together in moments of crises, as is shown during this current COVID-19 pandemic. I think a good example are virtual music festivals organized in Minecraft. Here, people are able to get together and socialize with others without leaving the safety of their own homes. But MVEs suffer from an important scalability challenge. For example, Minecraft, the most popular MVE, may support more than 126 million active monthly players, but it does so by heavily relying on replicating isolated instances, which themselves do not scale beyond a few hundred players, which means that the total number of players may be above 126 million. Each individual player cannot play together with more than a few hundred players at a time. And that has real consequences. For example, on the virtual music festival that I just talked about, because this festival had to be postponed because too many people tried to attend it. Only 100,000, which is nothing compared to 126 million, people tried to attend this festival, and that resulted in a total system crash. So given this, it's worth taking a look at what MVEs are and what we can do to make them more scalable. So to do so, we propose the definition of a modifiable virtual environment, or MVE. Now, MVEs are real-time, online, multi-user environments with a particular set of features. First, players must be able to modify the world's objects, such as their own player apparel. Second, players should be able to modify the virtual world's parts, such as its terrain. In an MVE, players should be able to build new buildings, destroy or create mountains, create mines, or move rivers. Third, players should be able to create new content by connecting components. For example, in Minecraft, players can build digital computers, and other MVEs allow players to build vehicles. Fourth, players should be able to interact with the world programmatically by submitting their own programs. Now, although the first feature is common in many online games, the combination of the last three features are what uniquely identify an MVE. Now that we know what an MVE is, let's take a look at how our work addresses their scalability challenge. And we do so with a threefold contribution. First, we model current MVEs and describe how they are deployed as cloud services and why that is not enough to address their scalability issue. Second, we present our vision of large-scale MVEs. In our vision, MVEs are serverless and run as a collection of services. Finally, we propose three challenging and timely areas of research to move towards our vision. Okay, so let's start modeling MVEs and their deployments. So MVEs are typically designed as a client-server architecture. In this figure, the client and server are the gray boxes. Inside the client and server are services which contribute to simulating the virtual world, and these are shown in blue. In this presentation, I want to focus on the MVE-specific features, which occur as server-side simulations. And this can be problematic because it makes the server more complex, and simulators are asked to compete for resources with the other components in simulators. Now, there are three common ways of deploying MVEs, but these do not address this issue. First, if a player has sufficiently powerful hardware, they can run both a client and a server locally. This requires the player to buy such hardware and then operate the game, which can be both expensive and complicated. Second, a game can be deployed as a service. In this case, the server runs in a cloud environment, and the player does not operate the game itself, but pays a fee to the cloud operator to do so. Finally, the third deployment method follows the streamed games model. And in this model, both the client and the server are moved to the cloud environment, and clients only run what is known as a thin client, which translates the user's inputs and sends it over to the actual client on the cloud, from which it receives back a fully rendered video stream that it can present to the user. So although these cloud deployments are advantageous, they do not address the increasing complexity of the server and the internal competition for resources of its simulators. Now this brings us to our second contribution, which is our vision for scalable MVEs. In our vision, MVEs become serverless, and they run as a collection of services. Now this figure on the right-hand side shows you a visual overview of our vision. And there's lots going on in this figure, so I'd just like to highlight certain aspects. First, in our vision, the game simulators and other computational intensive components, such as rendering, run as serverless services, where each service may consist of multiple serverless functions. Now, making these services serverless means that they can be professionally managed by the cloud operator and that they can be provisioned on demand by the game operator or game developer. It also allows independent scheduling of services, which can increase elasticity and address the scalability challenge that we identified a couple slides ago. Now, redesigning these systems as serverless also simplifies development because services can be modified and added independently. The second part of our vision is the use of specialized consistency models to communicate between services. And that's visualized in this figure through the state synchronizers. So online games traditionally suffer from rapidly increasing bandwidth usage for a growing number of players, and they can improve their scalability by choosing not to communicate all changes to everyone. But this introduces inconsistency. Now, inconsistency at the wrong time or place can ruin a player's immersion and experience, which is why we envision consistency models specialized for this use case, which are able to quantify and limit the inconsistency in the system. Another important part is using policies that selectively and temporarily allow inconsistency only in places where players are unlikely to notice. And these policies have to be determined by the game's developer, who knows which kind of inconsistency is tolerable and which kinds aren't. Now, the goal here is to improve scalability, but not reduce the player experience. Finally, we envision a differentiated deployment where services run on the user's device, cloudlets, or the cloud, depending on the workload, resource availability, and quality of service constraints. This allows the system to support resource-constrained devices when needed and reduce load on the cloud and core network when possible. So this could mean, in practice, running the rendering on a cloudlet to support a player playing on a mobile device, but it could also mean speculatively simulating the actions of digital logic components at a user device to reduce latency by basically hiding it. Okay, as our third and final contribution, we identify future research directions to move towards our goal of large-scale MVEs. First, existing work shows that serverless technologies are already capable of supporting some MVE or MVE-related services. For example, Pyren and Graphless are data and graph processing systems, allowing serverless game analytics. Now, game analytics is a MVE-related service that I cannot go into during this video, but it is described in our paper. But transforming entire MVEs to serverless systems requires additional research to push the limits of serverless technology. For example, we need to know if it's possible to create serverless systems for other MVE-related services, such as terrain generation, that I also won't go into now, but you can also read in our paper, and MVE services, such as the MVE simulators. Even if it's theoretically possible to make these elements serverless, the real-time nature of MVEs requires further work also to guarantee their non-functional properties. Other areas that require more work include communicating or sharing state between functions. Amazon recently announced a new Lambda feature that allows functions to mount shared file systems. And I'm curious to see and find out about its properties and what new kinds of functionalities that enables. Second, more research is needed in the area of specialized consistency models for MVEs. So there already exist consistency models that quantify and limit inconsistency. Most notably, the consistency unit consistency model. But more work is needed to adapt these models to match the properties of MVEs, which are real-time, have players joining and leaving the system constantly, and have consistency requirements that vary over time. We aim to develop these models in future work. Third, and finally, more work is needed on deploying MVE services on cloudlets. Here there are already promising results in the area of computational offloading, rendering, and game analytics. And it's worth investigating if we can use these resources for additional purposes, such as moving computational MVE service to the edge, but also for example, concurrent rendering for gameplay broadcasting. We also identify efficient resource sharing and the ability to store and cache data on cloudlets as important areas of future work. Okay, after this presentation, I hope you take away at least the following. MVEs are systems with more than 100 million users, are generally beneficial, but pose a scalability challenge. Our vision is to address this challenge by redesigning MVEs as serverless systems. This includes making MVE services serverless, using specialized consistency models to exchange state between services, and deploying services across user devices, cloudlets, and the cloud, depending on resource availability and quality of service requirements. Finally, these approaches already show promise and need to be explored further. Thanks for your time. Feel free to reach out to me with any questions or comments about this work, either again through Slack or using the contact information at the bottom of this slide.